Hey guys, welcome to Exact Equations. We're still in our series of learning ordinary differential equations, and here is one of my favorite parts of ordinary differential equations: exact equations. Now, a lot of you might have this conception about exact equations that wow, it's difficult, it's hard to understand, but I believe that after establishing the basic background you need to know about these exact equations, starting with this video, you will be able to know how to go about them. Okay, they are actually like the easiest part of ODE if you get to understand them. Now, some of the prerequisite knowledge that will be required to understand exact equations is you need to have come across something called implicit differentiation, okay, and partial differentiation. But if you have not done these before, don't worry, because of these lectures you will get to understand them, because I'm going to be citing examples. But my objective today is to introduce us to exact differential equations. And to introduce us to exact differential equations, first of all, we are going to consider a multivariable function. So the multivariable function we are going to be looking at is phi of x comma y, and it is equal to c. Okay, so consider a multivariable function phi of x comma y equal to c. So first of all, what is a multivariable function? A multivariable function is, as its name implies, it contains different independent variables. Okay, it could contain two independent variables, it contain three, could contain like infinite number of independent variables, or a particular finite long set of independent variables. Okay, some persons may still write this particular one with another symbol. Some might write it as f of x comma y. Okay, some might write it as w of x comma y. Some might write it as z of x comma y. But I want to use phi, okay, this Greek letter phi, to represent my multivariable function. So now that you've understood that a multivariable function is a function that depends on more than one variable, okay, I want to go further with our background. Now, we are considering that this multivariable function is actually a constant function somehow, because it is equal to a value c, okay, and c is a constant. So where c is a constant, now assuming that we want to find the total derivative of this multivariable function with respect to, say, x, for instance. So we want to find the total derivative of phi of x comma y equal to c with respect to x. So in other words, what we actually want to find, please permit me to call this equation 1. What we want to find is, we want to find d by dx of phi of x comma y. Okay, we want to find the total derivative of this particular function. Okay, so I will leave this as a 1b. So we are going to build from some basic theories that I'll be laying down until we get back to this point, equation 1b. So I just want you to sit back and follow me. So far, what have we said? We have assumed multivariable function phi of x comma y equal to c, and c is a constant. So our objective is to find the total derivative of this particular function with respect to x. In order to do that, since we have established that phi of x comma y is equal to c, then any change in this particular function, okay, any change in this particular function can be expressed by this equation. For instance, if you consider a change in C, a change in C can be taken by the principles of partial differentiation as the partial derivative of phi with respect to x times change in x plus the partial derivative of phi with respect to y times a change in y. Okay, so this is our equation for determining a change in this particular function phi of x comma y. Okay, so these particular symbols are the ones we use for partial derivative, and these particular delta symbols are the ones we use for expressing change. So you hear me call this delta, and you hear me call this particular one del. Okay, I think I have introduced this in our first video for ordinary differential equations, or in first 3 videos. Now, when you have a multivariable function, whenever a change occurs in that function, you always discover that the change that occurs in the function delta c will be partial derivative of the function with respect to, let me assume I have an f of x comma y comma z, and I want to find the change, okay, in that function. So the change in that function, or change in f, will be partial derivative of f with respect to x times change in x, then plus partial derivative of f with respect to y times change in y, plus partial derivative of f with respect to z times change in z. Okay, so this is how we actually determine the change in a particular function. Now remember, okay, that we want to find the total derivative of this particular function phi of x with respect to x. So at this point it makes sense, let me call this equation 2, it makes sense to divide through by delta x. Okay, so we are going to divide through by delta x. So in dividing through by delta x, I'll have delta c delta x becomes partial derivative of phi with respect to x plus partial derivative of phi with respect to y dot delta y delta x. Now when you see me write partial derivative of phi with respect to x, I actually mean partial derivative of phi of x comma y with respect to x, but I don't want to be writing this x comma y all the time, x comma y. All I just need to remember in my mind is that phi is a multivariable function of 2 independent variables, x and y in this case. Okay, so we are just going to be using for short del phi del x and del phi del y respectively. Is that okay? Now we have succeeded in dividing through by delta x. Now another assumption we need to make is that, okay, a change actually occurred in this multivariable function. Now what if we make that change very small? That is, by very small I mean the slightest occurrence of that change. Okay, very small. And how do I model that using equations? I'll say if delta x is very small, for instance if delta x tends to 0, then by the process or by the definition of calculus, okay, as delta x tends to 0, you discover that any ratio of delta y delta x will actually approach dy dx, and similarly your delta c delta x will approach dc dx. Is that okay? So we can now replace delta y delta x with dy dx and delta c delta x with dc dx in this particular equation. I can call this equation 2b. So if I replace it, you now discover that I have dc dx is equal to delta phi delta x plus delta phi delta y del phi del y, sorry, then you have dy dx. Okay, so you have del phi del x plus del phi del y and dy dx. So this is equation 3. So you have to recall that c is a constant. Okay, c is a constant. C is a constant. Since c is a constant, what happens when you differentiate constants? is actually 0. So we are now going to have 0 is equal to delta phi delta x plus delta phi delta y dot dy dx, and this is equation what? 4, for instance. So this equation 4 is actually the total derivative of our function phi of x comma y with respect to x. So let me take us back to where we said it. In our equation 1b, our objective was to find the derivative with respect to x of phi of x comma y. Okay, and this is what we have at equation 4. Now let me show you something. We said that our phi of x comma y is equal to c. So when you are differentiating with respect to x, the total derivative of phi of x comma y is as if you're differentiating with respect to x, c. Okay, so the derivative of phi of x comma y with respect to x will be equal to 0, and this whole place that you're seeing here is what we have in this particular hand over here. So the total derivative of this particular function with respect to x is given to us as in equation 4 as del phi del x plus del phi del y dot dy dx, and the total derivative is equal to 0. So this is usually the case with multivariable function. If you want to find their total derivative, okay, you can actually get it by using this particular approach that we have established, okay, still in equation 4. Now there's something interesting happening here in this particular equation, and you can see that initially phi of x comma y dependent on two variables, which are x and which are y. So in the course of our obtaining the total derivative of phi of x comma y with respect to x, we now stumbled across this term dy dx. So someone can say, wow, interestingly, I can actually make dy dx the surrogate of the formula, and I can actually find dy dx from this expression. So can we go ahead and make dy dx the surrogate of the formula? So if we want to find dy dx, we'll take phi of del phi del x to the other side of the equality, and we'll have negative del phi over del x. So if we divide both sides by, this is to find dy dx. So if we divide both sides by del phi del y, we'll have dy dx is equal to minus del phi over del x divided by del phi over del y. So this is the formula for finding dy dx for a multivariable function. If you want to find dy dx for a multivariable function, another name for a multivariable function, another rough name for a multivariable function is an implicit function. Okay, so if you want to find the dy dx for an implicit function, all you need to do is to try to obtain the derivative of the implicit function with respect to x, partial derivative, minus the partial derivative of the implicit function with respect to x divided by partial derivative of the implicit function with respect to y. So you don't have to worry. In another video just after this one, I'm going to refresh your minds on all of this. Now you might be asking me, why am I taking us through all these particular processes? Why do we have to go through these steps? It's because if you understand it in this way, trust me, you have known exact equations forever, for life. Okay, so it's good to know what brought about the exact equation. So this is how to obtain dy dx, but dy dx is not just the important thing in this particular equation. Dy dx is just of secondary importance. The primary importance, or the place where I'm going to be laying more emphasis to, is this equation 4, and I want to modify the appearance of equation 4. So in equation 4, we had del phi del x plus del phi del y dot dy dx is equal to 0. Now permit me to multiply through by dx. If you multiply through by dx, you have del phi del x dx plus del phi del y dy is equal to 0. So can you see something is happening? So let del phi del x be m and del phi del y be n. So if you let del phi del x be m and del phi del y be n, this is equation 5. What will happen then? In place of del phi del x, we'll have m dx plus, in place of del phi del y, you have n dy is equal to 0. Now this is the form of exact equations that you normally see in your textbooks, right? This is the form of exact equation that you normally see in your textbooks. So now you know where we are coming from. Anytime we say m, you'll be wondering what exactly is m. M actually is the partial derivative of our multivariable function with respect to x, and n is the partial derivative of the multivariable function with respect to y. Okay, and the test for exactness is that our partial derivative of m with respect to y this time around should be partial derivative of n with respect to x. Now, if I am to break what this particular thing means, the partial derivative of m with respect to y, remember what m is initially. M is what? Del phi del x, and this should be the partial derivative of n with respect to x. And what is n initially? N is del phi del y. Is that okay? So if we solve this particular thing together, what we're going to get is del 2 phi over del y del x should be equal to del 2 phi over del x del y. Now, if it happens to be that there is symmetry in your del 2 phi over del y del x and del 2 phi over del x del y, which is commonly the case in most implicit functions, if there is a symmetry and if these two are equal, then it means that your equation, this equation 6 over here, is exact. Is that okay? So if the whole summary of this particular thing over here is my, okay, my is just the partial derivative of m with respect to y. This is a short form of writing it. So if my is equal to nx and nx is the partial derivative of n with respect to x, then equation 6 is exact. Okay, so this is a brief introduction to what exact equation is all about. So you know where we are coming from when we say m and when we say n, and when we write this particular equation over here, when we write it in this form, you exactly know where we are coming from. Now the key highlights I want you to take note of is equation 6, very important, and the crucial fact that m itself is the partial derivative of the multivariable function with respect to what? X is the partial derivative of the multivariable function with respect to y. If you can know these particular things here, 1, 2, and this particular form over here, if you know these particular things, then trust me, you've actually simplified your knowledge of exact equations to a great extent. We'll see how to apply all of these later, okay? So you don't want to worry. So usually when we are giving exact differential equations, you'll be asking yourself, what is the objective? So our objective is to determine back the multivariable function. We want to determine the multivariable function, and remember, the multivariable function itself is like a constant function in the sense that that multivariable function is equal to c. So in your statement to solve exact equation, you have to start with saying that the multivariable function I'm looking for is actually equal to a constant. So please don't worry about how we're going to solve all of this now. We're going to have lots of examples to play with, but in the next video I'm going to teach us implicit differentiation using the formula that we have derived over here in this place. Okay, I'll teach us implicit differentiation, and I'll refresh our knowledge on partial differentiation. Now, the essence of doing it is that when we solve exact equations, we are going to verify, or we are going to test for the viability of our solutions by carrying out partial implicit differentiation again. If we carry out implicit differentiation, we should be able to get back the differential equation that we are given. Okay, so that's the reason why I'm going to spend some time in the next video after this one to show you how to do implicit differentiation in a new and in an improved way using our knowledge of partial derivatives. So this is very important, but I hope you've learned a lot by watching this video. This is a brief background to what exact equations is all about. A condition for exactness is that my should be equal to nx. Now, don't confuse something here. M itself is partial derivative of your multivariable function with respect to x, and n is the partial derivative of your multivariable function with respect to y. But if you want to check for exactness, you kind of like have to swap the polarity somehow. So you differentiate m, which is initially a derivative already. You differentiate m with respect to y partially, and you differentiate n with respect to x partially. M and n are initially derivatives, as we can see from this particular point. M and n are initially derivatives from over here. So if you're differentiating them again with respect to y and with respect to x, you're actually like going to get a second derivative term, as you can see here. So if you find out that the my is equal to the nx, then that equation, in equation 6 that you'll be giving, is exact. Please, it must be in this form, and I have to emphasize that there must be a plus sign here. So if there is no plus sign here, you have to look for a way to make a plus sign appear so that you get the right expression for m and the right expression for n. So thank you for watching this video. Please, I look forward to seeing you in the next video, in the next class. Don't forget to like, subscribe, and share. If you've benefited from this video, share to your friends, and I hope they will also share to their friends too. So thank you for watching, and see you next time. Peace.